This is an example of a logistic equation, mainly to do with populations, and basically the model looks a little bit like this. It's saying that the rate, dp dt, is the rate at which the population is growing, is equal to some factor times the present population. This some factor is sometimes called the growth factor. And that this rate is the growth factor times the population minus another factor k, which we'll call the decay factor, times the population squared. So the rate at which the population is growing is obviously with populations that there is some factor by which it grows, and then there is some factor of death rates and all sorts of things that make the population decrease. So the overall rate at which the population is growing, this model says, is the rate of the growth factor times the present population minus the decay factor times the population squared. So let's look at an example, and we've got dp dt is equal to 3p outside of 1 minus p, and we know that p of 0 equals 2. Okay, so we're asked to solve and find an equation for p. May not look initially like it's separable, but we can put a bracket around that. So it's 3 times p outside of 1 minus p. All of this contains p, so if we can get that over to one side and leave the 3 where it is, we've separated. So it's an example of a separable differential equation. So we get dp over p outside of 1 minus p is equal to 3 stayed where it is, and we'll bring the dt up. Now we can integrate with respect to both, on this side with respect to p and on this side with respect to t. Okay, now this is an example of a method we've done before called integration by partial fractions. So we can split this up as a over p plus b over 1 minus p. We can then combine these two together by making the denominators p outside of 1 minus p, find values for a and b, and we get a equals 1, b equals 1. I'm not going to go through that now. So this left-hand side of my integration becomes the integral of 1 on p dp, because a is equal to 1, so it'll be 1 over p dp, plus the other fraction, b is also equal to 1 minus p dp, is equal to the integral of 3 dt. Okay, when we integrate 1 on p, we get ln p plus, now the fact that that's 1 minus p on the bottom, we need to have p minus 1, so we multiply here by top and bottom by negative 1, and then we'll get p minus 1 there, but we'll get negative 1 there, so that will become a negative. So instead of that I'll write negative. The integral of p minus 1 will be ln p minus 1. We don't have to worry about absolute values here because we're talking about a population. Population always positive. Equals, now the integral of 3 dt is just 3t plus some constant of integration. Okay, so we've got ln p minus ln of p. When we're subtracting logs, we divide. So that'll be p over p minus 1 is equal to 3t plus c. We can take exponentials of both sides, and we get p over p minus 1 equals e, taking exponentials of both sides will become 3t plus c, will be e to the 3t times e to the c. Adding indexes, you're multiplying, and that'll be equal to, instead of e to the c, we'll make that equal to k, another constant, e to the 3t. Okay, so that's probably worthwhile just putting to one side because we might need that a little bit later on. So we've got p over p minus 1 equals k e to the 3t. Now we're after a function in P. We've got P over P minus 1 equals that. So we've got to rearrange this to get P as a subject. I think doing this, we could actually multiply both sides by P minus 1 and would be left with P on the left would be K e to the 3t outside of P minus 1 equals P times K e to the 3t minus K e to the 3t. We need to get all the p's over to one side, so take this over here and we get P minus P K e to the 3t equals minus K e to the 3t. P is common to both those two terms here, so P outside of 1 minus K e to the 3t equals minus K e to the 3t. Now we can divide both sides by 1 minus K e to the 3t. That'll leave us with P. We'll just take that over the other side, but it goes down the bottom, minus K e to the 3t over 1 minus K e to the 3t. Now, we are given some information right at the start as when t is equal to 0, that P is equal to 2. Okay. So that will allow us to work out a value for K. And if we go back up and have a look here, if I put P equals 2 in here, I know that I can put T equals 0 there. So using this one here, we've got 2, so you know P of 0 equals 2. So P is 2, so 2 over 2 minus 1. 0 for t equals K e to the 3 times 0 is 0. So e to the 0 is 1. So you got K is equal to 2 minus 1 is 1, 2 on 1 is just equal to 2. So K is equal to 2. So we get P equals negative, K is equal to 2. So we get negative 2 e to the 3t over 1 minus 2 e to the 3t. Alright, now just as an extension of that, what happens as t approaches infinity? Another way of looking at that, because this is a population model, and what happens to the population in the long term? In the long term is as t approaches infinity. Now, as t approaches infinity, we're going to have to see what happens when we substitute infinity in here with e to the 3t. One way to look at it, we can say that we can take e to the 3t outside the top and the bottom and cancel it down. So we've got e to the 3t outside of negative 2, e to the 3t outside of 1 over, now e to the 3t, what have we got to multiply to get 1? 1 over e to the 3t minus 2. Now we can cancel those down. As t approaches infinity, 1 over 3 to the very large number, that's going to be a very large number, so all that's going to go to 0. So therefore, P is going to approach negative 2 over negative 2, which is just equal to 1. So in the long term, we can say that P approaches 1 as t approaches infinity. So just going back again, this is an example of a logistic equation. There are other models similar to this, but it's an example of a separable differential equation. We get all the p's on one side, the other terms that don't contain p on the right-hand side. Use any method that we've learned up until now. One of them was by partial fractions, splitting it into partial fractions. We then were able to integrate. We're then able to make p the subject, in this case. We were given some initial conditions which allowed us to work out the constant of integration, substitute in that constant of integration, and we came up with an equation for P, the population at any time t. And then, just as an extension to that, we were asked to look at what happens as t approaches infinity. E to the 3t is a factor top and bottom, even though it doesn't look like it there, but that allows us to, as t approaches infinity, 1 over 3 to the infinity will approach 0, and you get minus 2 on minus 2, so p will approach 1.